This diagram shows the solar system exactly how most of us learned it in grade school. We picture a massive, heavy sun bolted directly to the center of space, with the planets tracing perfectly flat, concentric circles around it. In physics, the shape of an object's path is never an absolute truth. The trajectory you see depends entirely on the frame of reference of the observer watching it happen. Albert Einstein demonstrated this using a simple yet profound thought experiment. If you stand inside a moving train car and drop a stone, it appears to fall in a perfectly straight line down to your feet. But if an observer stands on the station platform and watches that exact same train speed by, they see the dropped stone fall in a long, curved parabola. Apply that exact logic to our solar system. The moment we step off the moving train of our local neighborhood and shift our perspective into deep space, those neat circular loops completely shatter. To understand how the Earth actually moves, we have to unbolt the sun from the center of the room and rebuild our planet's true path, layer by complex layer. First, Johannes Kepler proved with observational data that planetary orbits are not perfect circles. They are stretched out into ellipses. Then, Isaac Newton showed us that gravity is a two-way street. The sun pulls on the planets, but the planets pull right back, meaning the sun is not fixed to the fabric of space. Massive gas giants, particularly Jupiter, carry so much heft that their gravitational tug actually drags the sun off-center. Instead of Jupiter orbiting the sun, both bodies orbit a shared center of mass called a barycenter. This balancing point sits just outside the sun's surface, causing the star to wobble in a tight circle. With the anchor of our solar system in a constant state of jittering motion, Earth's orbit is already warped from the inside out. Even with these wobbling ellipses, the loops never perfectly close. The gravitational field near the sun is so intense that it actually bends the geometry of space. Einstein's general relativity predicts a phenomenon called precession. Precession is a gradual shift in the orientation of an orbit over time, a quirk of gravity that astronomers first proved by measuring the slightly skewed rotating path of Mercury. Because of precession, the entire orbital ellipse slowly rotates. With every single pass around the sun, the stretched-out path shifts its angle slightly, tracing out a sprawling, overlapping spirograph. Relativistic precession guarantees that a planet never returns to its exact starting point. The idea of an identical repeating year is a local illusion. Now we need to drastically shift our frame of reference one more time, zooming all the way out to the macro scale of the Milky Way. Our sun is a thin disk star. A thin disk star is a star whose orbit is confined closely to the dense, flat plane of the galaxy, and ours is hurtling through that plane at hundreds of kilometers per second. The sun's immense forward momentum drags the Earth along, transforming its flat orbit into a massive, trailing corkscrew through the void. The sun's path is dictated by the rules of galactic dynamics, where the collective gravitational pull of hundreds of billions of stars, vast clouds of gas, and unseen dark matter steers its motion. This collective gravity causes epicyclic motion. Instead of flying in a smooth circle, the sun wobbles radially, drifting inward and outward from the galactic core. Simultaneously, it bobs up and down, passing vertically through the galaxy's flat plane, like a dolphin riding a wave. The Milky Way's mass physically steers our entire solar system through a chaotic, three-dimensional obstacle course. The flat, simple orbit we started with is completely gone. When you stack all these mechanics together, the elliptical stretches, the barycentric wobbles, the relativistic precession, the forward galactic drag, and the vertical bobbing, you get the true shape of Earth's motion. In reality, Earth never occupies the exact same point in physical space twice. We are carving a chaotic, multi-layered, non-repeating spiral path through the dark. Seeing the tangled geometry of our actual path makes it clear how swept up our planet is in the larger motions of the galaxy. But mapping this complexity is exactly how we find our place in the dark. We can track the gravitational fields that steer us and predict the ripples we'll pass through in the future. Our twisting trajectory through the void is the physical signature of the same gravity that built the Milky Way. By tracing it, we aren't just watching the universe,
we are understanding the mechanics that keep us part of it.